1 div 2 area, class 1 would be a gas, and the div 1 area would be the gas is normally there. It's present all the time. So now we need to describe what type of gas it is. It's in a group A, B, C, or D gases. NEC Article 500.6a talks about these gases. Groups indicate the degree of hazard. Groups A, B, C, and D are classified by chemical families as shown in NFPA 497M and 325M. The important factor in classifying a gas or vapor by group is how much pressure is created during an explosion. Group A, acetylene, creates the most pressure, with Group B, hydrogen, next. So what this chart is actually showing you, it doesn't really show you pressures. It shows you lower explosive limits and upper explosive limits. So here you have Group B hydrogen. If the volume of hydrogen with respect to air is less than 4%, then it is not a hazardous area. If it's above 75%, then it is a hazardous area, and that's what this chart is trying to show you. So you could theoretically, and people do this, add mechanical ventilation of fresh, clean air from a safe area, and they dilute the area where it has the hydrogen so that it's below 4% hydrogen. In fact, they do it to 25% of that value, which is 1% hydrogen. So if you diluted an area that normally would have some amount of hydrogen between 4% and 75% and reduced it to 1% hydrogen, then you could say, oh, well, then that area is no longer a div 1 location, it is now a div 2 location. There's some arguments about, can you take an area all the way to a general purpose area, and that's a little harder to do, because what if the mechanical device fails? Then you have, again, a div 1 location. So typically with a mechanical ventilation device, a div 1 area is allowed to be a div 2 area, but not a general purpose area. Group A is acetylene, Group B is hydrogen, Group C is ethylene, Group D is propane. And in the NEC, you'll find a lot of these, or also in the NFPA 497, a list of all these gases, and it'll tell you what groups they are. You rarely have to determine what group it is, but if you do have to determine that, you can find that in IEEE standards as well. Okay, so we talked about Class 1 gases, which were A, B, C, and D. In Class 2 areas, you have dust, and you have groups E, F, and G. So here you have, and it's in NEC Article 500.6b. Groups indicate the degree of hazard based on the electrical resistivity from table on the right. Group E, atmospheres containing combustible metal dust. Group F is atmospheres containing carbon black, charcoal, coal, or coke dust. And Group G, atmospheres containing agricultural and other dust, such as sugar, things of that nature. So you can see Group G at the top, you have cake mix, cocoa, powdered sugar, grain dust, flour, cornstarch, flour under stress. And then Group F is crushed charcoal, printer ink powder, active carbon, charcoal, wet coke, wet charcoal, wet petroleum coke, and wet coal, or solid carbon and solid graphites. And then Group E is your actual metals, your metal dust. So here we have, I just grabbed a sample chemical, and you can see acetic acid is Group D, and it has a case number. It's a type 2. We haven't really talked about type 1 or type 2. It's got a flash point of 43 degrees C. It has an auto ignition temperature, AIT, of 464 degrees C. And it has lower flame level of 4.0%. The lower flame level and the lower explosive level are very similar, and I think for all gases they're about the same, except for hydrogen. So auto ignition temperature is a really critical point you need to remember. This is the minimum temperature required to initiate or cause self-sustained combustion of a solid, liquid, or gas independently of the heating or heating element. So when you come up to a a lamp or a motor or a resistive heating device, if the surface temperature of that piece of electrical equipment actually exceeds the auto ignition temperature, then it could explode. Well, you're thinking to yourself, well, 464 degrees C, that's pretty hot. Well, it is, but there are things that can get hotter, especially like a resistive element from a heater. They can easily get up into 1,000 degrees Fahrenheit, just skin temperature of the sleeve itself. Next, we're going to look at the flash point, the minimum temperature at which a liquid gives off vapor in sufficient concentration to form an ignitable mixture with air near the surface of the liquid as specified by test. So here you can see the acetic acid has a 43 degrees C flash point. I went ahead and included a few other ones. One of the most common is methanol or methane, and methane is a D. It's a gas. Its flash point is minus 223 degrees C. Its auto ignition temperature is 630 degrees C, and its percent lower flame level is 5%. Liquefied petroleum gas is another one. So it's a D. It's type 1. And its auto ignition temperature is degrees C is 405 degrees C. So if I knew I had petroleum gas out there, or liquefied petroleum LPG, then I would know that it's a class 1, and then depending if it's going to leak normally or abnormally, would be a div 1 or div 2. It would be group D, and then its temperature rating would be probably a T3, which we haven't really talked about yet, but we'll get to that soon. And that T3 has a lot to do with that auto ignition temperature. Conditions necessary for ignition. In a Class 1 area, the following 3 conditions must be satisfied for the combustible material to be ignited by the electrical installation. A combustible material must be present. It must be mixed with air in the proportions required to produce an ignitable mixture, and then there must be a release of sufficient energy to ignite the mixture. So if we have a combustible material such as LPG, and it is below 5% or just above 5%, less than 75%, then we have a gas that could explode in this environment. If it's actually below 5% or above 75% with percent of volume of air, then it might not explode. And then there must be a sufficient release of energy to ignite the mixture. So that could be a heat source above its auto ignition temperature, or it could be an arcing, a breaker opening or closing. Once the breaker opens, it arcs. And when it arcs, that's the sufficient energy to ignite the mixture. We'll talk about this later, but there are things such as IS barriers, and these IS barriers actually limit the energy sufficient to ignite the mixture. 2 watts is, if you have a source that is 2 watts or less, that will not ignite hydrogen. So here's the explosive triangle. If you have the 3, again, fuel, oxygen, or ignition, if the fuel is flammable gases, combustible dust, or flyings or fibers, oxygen, air, or oxidizing atmospheres, and the ignition could be arc, spark, or heat generated by equipment. If all 3 of these occur at the same time in the right mixtures, then the explosion occurs. So the idea is to either 1, contain this explosion, or 2, remove 1 or 2 of the combinations, the 3 combinations, so that it won't explode at all. If we remove the fuel, how could we remove the fuel? We could use a pressurized enclosure. We haven't talked about that yet, but when we get to it, that's what they're doing. They're actually putting purge air into the enclosure so much that there's no way that fuel can actually get into the enclosure and ignite. So that would be an example of removing one of the three. Removing ignition source would be an IS barrier, an intrinsically safe barrier. To remove the oxygen and fuel source would be maybe encapsulation, where they actually encapsulate a transformer. Oil-filled transformers would be an example of that. We talked about NEMA 7 enclosures. A NEMA 7 enclosure is actually what they call a crock box. This is a heavy-duty aluminum box. If you had like a 4-foot long box, maybe 2.5, 3 foot wide, maybe 12 inches deep, that box would weigh about 1,000 pounds or so. It's a very heavy-duty box, and the reason it's so heavy is it actually allows the explosion to occur inside the box, inside the electrical equipment. When that occurs, the pressure inside the box builds up real high, and in these machine flame paths allow the gas to escape. And as it escapes, it has a refrigeration effect which cools the gas so that by the time it hits the environment on the outside, it is below the auto ignition temperature. And here a NEMA 7 box is an explosion-proof apparatus. It's suitable for a Class 1 Div 1 location, an enclosure that will withstand an internal explosion of gases or vapors and prevent those gases or vapors from igniting gases or vapors in the surrounding atmosphere outside of the enclosure. So we'll look at some pictures of those later, but that's what a NEMA 7 box does. You have the right air and gas mixture in the box. It could be they did maintenance on it. They opened up all the bolts. They were working on the panel. When they closed it, they had the right air and gas mixture. When the motor starter started, boom, that's the ignition source, and the actual panel it'll hiss at you, and flames will come out of the side of it. But because of those flame paths, and if you have all the bolts on that box, it will not explode the gases around, in the surrounding atmosphere. And that's a big point right there. A lot of times when you go out to some areas, they have all the bolts missing except one or two. And their idea is they don't feel like removing putting all those bolts back in. Well, if they do that, what they've done is they've actually created a hazardous condition, because that explosion could occur and blow that cover right off the box. And that cover is extremely heavy. So if you have a area or a site and you're a maintenance guy and you notice that, hey, there's some bolts missing from some of these NEMA 7 boxes, make sure you get them all installed with the proper bolts from the manufacturer. Don't substitute those bolts. You have to get them from the manufacturer. Another thing about these boxes is the only person that can drill a hole in these boxes is the manufacturer. So if somebody orders a box and they don't have enough holes in it, don't let them drill it in the field. They must go back to the manufacturer and get an authorized rep to drill the proper hole in that box. And then here's some pictures of some explosion-proof boxes. See this thing right here? This is actually a gasket. It's an O-ring, and that O-ring gasket combination makes this a NEMA 7-4. So it's no longer rated just for indoors. It's actually rated for outdoors as well. And here's a nice cutaway to show you how thick this box really is. It's a very heavy-duty box. And when they manufacture these boxes, they actually can have air pockets in them, and obviously try not to, and that's why you don't want somebody drilling into this box that's not authorized, because they might miss that there's an air pocket inside that box. And if there is an air pocket in that box and they drill into it, then they might not get the proper threads. There's certainly 5 to 7 threads per inch that you have to follow depending on the area. So you need to follow that and make sure you get your box manufacturer involved. An explosion-proof enclosure must be able to withstand the internal explosion pressure, Prevent the propagation of flame through any joint or opening to the outside of the enclosure. Maintain a low external temperature that will not ignite the surrounding flammable atmosphere. And then, of course, there's UL tests that must be followed. So when you buy one of these boxes, make sure it is UL listed per UL 1203. An explosion tests are performed to determine the maximum pressure and propagation effect. Hydrostatic pressure test at 4 times the highest explosion pressure is used as well. And this allows them to make sure that this box is suitable for your area, because, like I said, there's actually an explosion that will occur inside this box, and it'll hiss. It'll push the air. The high pressure explosion will come out the sides, the labyrinth paths, and the machine surfaces, and it cools itself. An explosion-proof equipment joint. There's different ways. Obviously we looked at flat joint construction. There's also threaded joint construction, or a labyrinth path construction. You could have a precision Acme conical thread construction. Close tolerance shaft construction would be like for a valve. Interlocking concentric ring construction. So here in this picture right here provided by Appleton, that's actually a threaded construction. And one thing you'll notice about these enclosures, or these GUATs, GUATs, or GUALs, they are, let's say if you order a steel box or an iron box, cast iron box, the actual lid will be aluminum, and I always wondered about that, but one of the guys that told me from the manufacturer said that the lid is always aluminum because you could drop it, and so it's a copper-free aluminum, and obviously copper-free aluminum, when it hits the ground, will not create an arc ignition source, so that's why they all have aluminum lids. Another thing is you only need 5 full threads or 7 full threads, depending on your area, on that box. So you don't have to torque that box, the lid down. All you have to do is bring it up to flat to its surface, to its gasket, and then just kind of hand tighten it. You don't have to actually torque on that box or that box lid. And then here again is another example of that flat joint or ground flat joint construction. Here we have inside the enclosure, we have the hot flaming gas. As it passes through this machine surface, it cools itself. It has a refrigeration effect, and it cools the escaping gas. So this is another problem if you don't put the bolts in, or if you don't have the proper person drilling holes in this box. Because if you don't drill them properly and you don't have the right threads and the construction, then you can create a situation where you've created a hazard unwittingly. This is a threaded joint construction. So here you got the hot flaming gas down here. Passes 1, 2, 3, 4, 5, and then it cools here. So by the time it gets through this, and that's another reason why these boxes are aluminum. One, they're heavy. You can actually have these made out of stainless steel, but as that hot flaming gas passes through, the metal absorbs that heat and allows it to cool. Here's some more pictures. Here you again have a flat ground surface with an O-ring. See that gasket right there? So that's a NEMA 7, and it's probably epoxy coated, so it's a NEMA 7 4X. Again, the 4 is the gasket, the 7 is the heavy-duty explosion-proof enclosure, and the X would be if it was painted with an epoxy coating. So here you can see an epoxy coating instrument enclosure. And then they have a special threads already pre-drilled. One thing that's recently come up is the actual couplings. Those actually have to be rated now. It used to be years ago they weren't rated, but now REs and REAs all have to be rated. They have to be stamped for the area. So here you can see different enclosures as well. This is threaded construction. And if it had another so this would be a GUAT if it had another conduit coming out of this side. If it had a conduit coming out of all four sides, it would be a GUAX. So here's an an enclosure, an NEMA 7 enclosure under test. So you can see it's a very violent explosion inside that box. So, and then they also have a breather here. And something interesting about these enclosures is they do actually breathe. So as the temperature of the box inside changes and the outside changes, they collect water is one thing. So you want to make sure that they can drip the water out of them, and they actually can breathe. So as they're breathing, they can actually create a hazardous gas mixture, and then the explosion can occur. It seems kind of odd that they would even allow something like this to happen, but that's how it's been for years. And we still use them today. These enclosures have to be rated for the environment. And then here's a labyrinth path. So you can see here, it actually comes through this way and then comes out. So they've created a labyrinth. And here again, they've got another labyrinth. And then here they have threaded conduit entries. So again, you need 5 to 7 threads depending on the area that you're installing the equipment. Another area or something that you need to know is you can't use you have to use special threads for hydrogen. Areas that are rated for hydrogen group B are different. The threads that they install are different than the threads that they use for group B or group D areas. So you need to be aware of that. That's why you always want to have a manufacturer's authorized rep or the manufacturer himself drill all the holes in these boxes. Don't let anybody drill a hole in your box. Here we have a close tolerance shaft. So here, this is just a like a valve handle or something like that. So here is a summary of classes and groups. Again, we have class 1 is for flammable vapors or gases. And then you have in class 1 group A, B, C, and D. Class 2, combustible dusts. And then group E, F, G. And then class 3 is fibers and flies. And there's really, there's no groups for class 3. The NEMA enclosures, you got NEMA 7 is suitable for class 1, group A, B, C, and D. A type 9 is class 2, so group E, F, and G. And there are no provisions for NEMA type for class 3 locations. So if you have a methane gas, it's a class 1 area, and you need to use a type 7 enclosure. Now, I'm not saying you have to use a Type 7 enclosure, but if you were going to use a NEMA enclosure to a large explosion-proof box, you would use a Type 7 enclosure is what I'm saying. If you have a Class 2 area, such as a coal refinery or a coal mine, then you would use a Type 9 enclosure, NEMA Type 9 enclosure. And if I recall, a Type 10 enclosure, which we didn't talk about, is for mining. Okay, something that needs to be discussed here is something called pressure piling. Here we have two explosion-proof boxes. We have a NEMA 7 or a NEMA 7 box here, and we have a NEMA 7 enclosure here. This round enclosure right here is actually a circuit breaker or a motor starter. So when the actual explosion occurs here, it builds up a great deal of pressure. That flame front passes through here and it builds up to 1.5 times the pressure in here. It can be so strong it can blow this lid right off. So you need to be aware of that. When this enclosure right here explodes, it can literally blow the other enclosure up. I was listening to a guy tell me a story of an electrician who had come up to a normal general purpose panel board, and he would open and close the circuit breakers. And as he opened and closed the circuit breakers, he heard the front of the panel actually rumble. And he thought, well, that's really weird. And he couldn't figure it out, so he finally called some engineers out there, and they investigated. And what they found out was the installing contractor had run a conduit and found another conduit that was a 4-inch conduit, tapped into it, and kept running his wires. Well, what he did was he actually tapped into an explosive environment. And by doing that, he allowed gases to flow up in this line, and then when this electrician was opening and closing the circuit breaker, he was actually providing the ignition source. So he's lucky he didn't get hurt, and the installing contractor had to go back through there and install a seal. That's what you do, is you install a conduit seal to stop this. And basically what you do is, if you have two enclosures here, you need to install a seal within 18 inches of each of these enclosures. If this enclosure is within 36 inches of each other, then you can install one seal in the middle of them. But if these enclosures are 100 feet apart or something, you need to put go ahead and put a seal right here, a conduit seal right here within 18 inches of this enclosure, and a conduit seal on this side within 18 inches of this enclosure. And this will prevent the pressure piling from occurring. You're actually controlling the explosion within that enclosure. And this is what a seal looks like, a conduit seal. You can see the wires allowed to pass through here, and here they have a breather drain as well. And these seals, you order them either vertical or horizontal, or you can order them where they can go vertical or horizontal. And another thing you need to know about these seals is ordinarily conduit, you fill it to 40% conduit fill, right, for wires. A standard seal, can only be filled to 25%. So if you're going to follow the old 40% rule, which is a good rule, you need to buy what they call an expanded seal. So make sure you follow that. That really gets a lot of people, they get caught up on that. So another thing about these seals is they have to be filled with a compound. It's a special compound that prevents that flame from passing, or prevents gases from leaking through this conduit. So again, you require within 18 inches of an enclosure containing arcing or high temperature devices, Class 1, Div 1, and Div 2 locations. Requires a Class 1, Div 1 location where 2 inches or larger conduits enter enclosures that house terminals, splices, or taps. So there's a lot of rules to where conduit seals have to be, and you need to make sure you follow the NEC and that they're filled properly. So they're required at Class 1 boundary where conduits leave the hazardous area. So if you have a non-hazardous area such as an MCC room, you're leaving that MCC room and going into a hazardous area, that's where you need the seal, right at the point where you leave you enter into the hazardous area. So anytime you have a hazard change, you need a conduit seal. UL requires that sealing compound and sealing fittings be of the same manufacturer. So if you buy a seal from Kraus-Heinz, let's say, then you must use Chico. Chico is Kraus-Heinz Industrial Compound. That's what that means. So if you buy something from Appleton, you need to make sure you buy the fill from Appleton. The depth of the sealing compound should be equal to the trade size of the conduit, having a minimum thickness of 5/8 inch thick. And I'll show you a properly filled seal in a minute. So here you have two seals that are properly filled. So at the bottom down here, you have a special fiber, wool fiber, I'm not sure really what it's made out of. I think it's a wool fiber. And then they pour the Chico in here. So you open this up, they pour it in here, and they have to properly spread these wires out. Now you can notice between these two fittings that one is larger than the other, right? So this one is for the 40% fill, and this one is for the 25% fill. Expanded fill conduit seal fillings can be used with a conduit system allowing up to 40% conduit fill. Standard conduit seal fittings are limited to 25% fill. So this, you're probably thinking, oh my God, do I have this problem in my installation in my plant? And chances are pretty good you do, because a lot of people don't realize this, and you need to make sure you check that. Another thing is these conductors have to be spread apart properly,